Hey folks, welcome to this episode on the gas law. Now there are a few gas laws that we're going to be looking on in this episode and the next. In this episode we're going to be looking at Boyles Law, Charles's Law, Gay-Lussac's Law, Avogadro's Law, and putting it all together, the combined gas law. Now as you can see, a lot of these deal with the relationship between pressure, volume, and temperature. We're also going to be looking at how moles fits into all of these relationships. Let's start off with Boyle's Law, and this is a relationship between pressure and volume. Now you can probably establish this relationship without any kind of experiments, just based on your daily life occurrences. But what we can say about this relationship is that it's inversely proportional, which means that as one increases, the other one decreases. Something that is directly proportional means that as one increases, so does the other. You'll find in a lot of these laws that we also have things that are constant. If we have too many things changing, then we don't really know what the direct relationship is. So when we look at Boyle's Law, we're keeping two things constant, temperature and the number of moles. So how can we describe this based on the kinetic molecular theory? Well, as we decrease the volume, so as we go from a container that maybe has this much volume to a container that has this much volume, what we're seeing is that if we keep moles the same, so if we keep the number of molecules in this the same, so 1, 2, 3, 4, 5, in the first case, these 5 have a lot of volume where they can travel. They might hit each other, they might not, they might hit the edge of the container. But there's a lot more probability for them not to be hitting anything. If we put these same 5 molecules in a container that has a lot less volume, the chances of them colliding together or hitting the walls of the container is a lot more. And so as we decrease this volume, the chance of collision increases with the container, and what that actually means, more frequent and more harder collisions, means that you're going to have an increase in pressure. And so this law is shown in the mathematical equation P1 V1 is equal to P2 V2, where P1 is the initial pressure, V1 is the initial volume, and here we have our final pressure and volume. So what you can see is that a lot of these laws actually have to deal with a change. So we're going to change one condition. For example, we change the pressure, and we see what the resultant volume is going to be. So as we saw over here, as we change the volume, we are going to see a change in pressure. So in this case, what we do is we're increasing the volume. So what we should see is a decrease in pressure, and so we do. We can see that our temperature is constant, and we can also see that the number of moles are also constant here. So what we should see is that if we increase the volume twice, or by 2, we should see a halving of the pressure. Next law is Charles's Law, which looks at volume and temperature. And this is the directly proportional relationship. And you can see that by the graph. It goes up. As one increases, the other one also increases. And in this case, we're keeping pressure and moles the same. Now, keeping pressure is the important thing here, because that's actually going to affect how the system works. Now, as we look at temperature and remember that we have a gas container full of these little gas molecules inside of here. As we increase the temperature, what are we actually doing? Remember, as we increase temperature, we're increasing the kinetic energy. Now, what does that mean? These gas molecules are going to be moving a lot more. They might be moving faster and hit with a stronger force. And so what we're doing is, if they start hitting with a stronger force, what we're effectively doing is we're increasing pressure. Oh, but wait. I thought we had to keep pressure constant. Well, we do. What's the only thing that can actually decrease pressure is that if we actually increase our volume. Now, this won't happen by somebody just increasing the volume. It's usually as a result of a barrier that can move up or down as a result of a change in pressure. So as we actually heated these molecules or particles over here, or atoms, and we started increasing pressure, well, that increase in pressure would actually start pushing against this barrier, causing it to move up and up and up, eventually restoring the original pressure. And so this is shown by the equation V1 T1 is equal to V2 over T2. Now, some people have a hard time with this equation because it's a fraction. So another way of expressing this equation that makes it easier to rearrange is by moving this up here and moving this up here. And what we effectively get is we get V1 T2 is equal to V2 T1. And now you can see it's a lot easier to actually manipulate to solve for one variable or the other. So as we saw, the temperature and volume relationship is that as we increase the temperature, the volume will also increase. The reason that the volume increases, for example, if we look at here, here's our temperature and we increased our temperature here, and as a result, our volume increased from here to here. Well, we kept moles the same, and we also kept pressure the same. And that's the reason why we kept pressure the same, is because as these things start getting hotter, they start hitting against the container more and more. It starts pushing this movable piston a little bit up to start relieving that pressure, and eventually it gets to a portion or a point where the pressure is the same as it originally started with. Next law is Gay-Lussac's law, and this looks at pressure and temperature, and it's very similar to what we just saw. As we increase our temperature, we'll also be increasing our pressure. Why? Again, as we increase our temperature, we're increasing the kinetic energy. More kinetic energy means more collisions. More collisions with the wall of container means a higher pressure. So that is our relationship in this case, and it really helps to know this law in order to explain Charles's law, the law that we saw before. Now, once again, because this is a directly proportional relationship, we have P1 over T1 is equal to P2 over T2. Again, if this doesn't work for you, you can express it in a different way. You put these T's at the top, and you'll get P1 T2 is equal to P2 T1. Again, making it a little bit easier to manipulate the equations. Now, what happens here is that a little bit different, is that if you look at our constants are volume and moles. So this is why as we increase temperature, our pressure is also increasing, because we're not allowing that volume to actually increase to stabilize the pressure. We're making it an unmovable barrier, so no piston, and just causing volume to be static. So as you can see here in this case, this piston that we have here is immovable, where it's going to keep in the same area. So as we actually increase the temperature of these particles, they're going to start moving a lot faster. You can see that by the streaks here. And as they start moving faster, they hit with more force over a certain amount of area, and that is going to be seen by an increase in pressure. So if we increase our temperature by 2, we should also see an increase in pressure by 2. And finally, we have Avogadro's law. And this relates volume and moles. And this is actually most seen in the balloon example that we saw before. If we had a balloon, and we had a small little balloon here, and we start blowing air inside of it, what are we actually introducing? We're introducing moles of oxygen, carbon dioxide, nitrogen, whatever. As we introduce moles, our balloon gets bigger. You're going to have more particles of gas inside of here. Again, if we want to make it even bigger, we're going to have to introduce more moles by breathing another breath in there, and we're going to get a huge balloon with a lot of particles of gas inside of it. So the more moles that we introduce into this balloon, for example, the bigger the volume is going to be. Now, there's one thing that we have to recognize, is that this balloon can accommodate more moles. It can expand its volume by being elastic. If we keep breathing into, for example, a bottle, there's only a certain amount of moles that can fit into a bottle until the pressure gets so big that it pops off. So in here, to kind of stabilize the pressure, our volume has to actually increase. And this is what we see in the equation. As we increase the number of moles, the volume will also increase as well, because remember, moles are just representative of particles. Particles are matter. Matter take up volume. So once again, if this equation doesn't work for you, you can have V1 and 2 is equal to V2 and 1. And again, here we see if we had a little area that we could introduce moles into here, we would be able to push this piston, this movable piston, upwards to relieve that pressure. So what you'd see in the interim is that you'd actually see a pressure that would be a lot greater. Yeah, you'd see a lot greater, but as we move this volume up, this pressure then starts to stabilize back and gets to its original value. Now, if we actually combine Boyles Law, Charles's Law, Gay-Lussac's Law, and we actually keep the number of moles consistent when we're talking about Avogadro's Law, we get something called the combined gas law. And what it states is that at a constant moles, the product of the pressure and volume of a gas is proportional to its absolute temperature in Kelvin. And again, we can see that, we can represent it using this equation here. Now, if we look at this equation of the combined gas law, we can actually see our different gas laws in action. We can see P1 V1 is equal to P2 V2. We can also see our P1 over T1 is equal to P2 over T2, and we can see our V1 over T1 is V2 over T2. So we can see all of our actual laws combined, and once again, if we keep our moles constant, we can also start including our Avogadros. Once again, if this equation doesn't work for you, we can put the t's up on the top, so we get P1 V1 T2 is equal to P2 V2 T1, and that will allow you to manipulate this equation a little bit easier down the line. Thanks very much for watching. See you soon.